it's a true CV because I will tell about him what I know in terms of his papers. But you work in a group of Stockholm, in a group of particles, and you look to dark matter candidates and look for supersymmetry. And in particular case, you look to the impact of evolution stars. I remember that. And but the nice thing about you, yes,
I did do.
Sorry?
I did do.
Yeah. Sure.
Now McGill.
Yeah. Okay. And then also you have some experience in stellar stars and stellar evolution in nuclear spectroscopy. You may be one of the persons with one of these papers. If you do stellar physics and evolution of stars like the Sun, you need to use spectroscopic data. And for sure you see these papers because it's one of the few papers that are very used to that in terms of spectroscopy. However, it's interesting to see all around physicists with a different background. And now is a position at the Department of Physics of McGill University, and I welcome you, and please go through your seminar.
Thanks very much for having me. So you've heard quite a bit this morning about stars and even the Sun as laboratories of particle physics. Well, if you came to Geordie's defence, which I think looking around at the places almost everybody did. I'm going to talk about a couple of fairly orthogonal ways to try and constrain different theories of particle physics using the Sun. So this is based primarily on these three papers. A lot of the stuff I'll talk about is the work of either Aaron Vincent, who you may hopefully see a bit of over the next couple of years. He was a PhD student at McGill. He's now a postdoc at Valencia. And also Hamish Silverwood, who effectively did his master's thesis with me, but is now doing a PhD at Grappa in Amsterdam. So hopefully you'll see a bit of these too. And also this paper here, which was done in collaboration with people from Stockholm, but also the IceCube collaboration. And I should say, it's a pretty small group. Just interrupt me and ask questions and start discussions whenever you want. Okay, so, first up, you want to understand why the Sun is actually good as a particle physics laboratory. After that, I'll talk about a specific piece of work looking at high-energy solar neutrinos and trying to say something about beyond the standard model physics with those. And then, assuming I have time, I'll go into this solar abundance problem. This is the current disagreement between helioseismology and spectroscopic determinations of the solar abundances. And an idea we had for potentially solving it using new physics, which turns out doesn't actually work, but was an interesting idea anyway. And I'll tell you why that doesn't work and sort of what constraints that gives us for other potential particle physics solutions to the solar abundance problem. Okay, so there are a lot of different ways you can use the Sun to actually try and say something about new physics. And the different ways really relate to the different areas in the Sun and the different properties of the Sun. So we've heard a lot this morning about using helioseismology or astroseismology with other stars to put constraints on exotic modes of energy transport. So in this case, you would expect the structure of the Sun to be modified slightly, particularly around the core, due to basically conductive energy transport by new particles like weakly interacting massive particles that would scatter off nucleons in the centre of the Sun and transport energy conductively. The other, probably most obvious way of using the Sun to constrain particle physics is to do it via the solar neutrinos. So in this case, you look for the neutrinos produced in the nuclear reactions in the core, and you can use those to say something about different neutrino theories. So, for example, the old solar neutrino problem, we saw that neutrinos oscillate, and you can also use these to start to try to say something about extensions to the neutrino sector. So sterile neutrinos, or exactly how strong the mixings are between the different neutrino families. You can also use these to try and say something about the temperature of of the sun, and we've also heard a bit about this morning. So this gives you a constraint on exotic energy transport modes in a similar way to helioseismology, in that you can start to constrain theories that have new heavy states that will carry energy conductively. You can also look for exotic neutrino production. So in this case, in both of these two cases, I'm talking about standard, relatively low energy, so like MeV kind of scale, solar neutrinos produced in the nuclear reactions. Whereas here, when I say exotic neutrino production, I'm talking about neutrinos with much higher energy, so GeV sorts of energies. And you might expect to get these if you have something like dark matter annihilation going on in the core of the sun. So in this case, the neutrinos will either come directly from GeV scale particles annihilating in the centre of the sun, or they'll come from the products of the annihilation. So you might annihilate into a quark-antiquark pair, which will then interact with the nucleons inside the sun and produce high-energy neutrinos that way. Or you may go to W bosons, which then decay to high-energy neutrinos. Another way you might hope to constrain new physics using the sun is actually directly through the solar spectrum. And this is stuff that is really only been explored, as far as I know, in this one particular paper that we've put out. And the idea here is that if you can come up with some kind of particle scenario that will cause an effective change in the opacity in the solar atmosphere, then you can potentially change the depths of the absorption lines that you create in the solar spectrum. And then finally, the other way that people use the sun to constrain new physics is to look for direct new particle production. So you've probably heard about solar Axion telescopes or helioscopes. And the idea here is that you just look for new particles that have been produced via some process either in the core of the sun or potentially a little bit further out, and then try and detect those particles here on Earth. So you want some theory that gives you a very weakly interacting particle, like an axion, that can be produced in the sun, but would then travel all the way out of the sun without interacting with the normal matter inside it. So for the purposes of this talk, I'm really going to focus on these two scenarios. This high energy neutrino production from dark matter annihilation in the core, and potentially also this modification of the solar spectrum from a new opacity source or sink. So I'll start off with the dark matter annihilation stuff. I should say that this is kind of an industry, really, whereas this is really very new. All right, we've really gone through this a lot this morning, so I'm not going to spend much time talking about what dark matter needs to do. Basically, you want it to be massive, and you don't want it to interact too much, and you want to have the right amount of it in the early universe. There are a lot of good candidates that will actually do all of this for you. The prime one really is weakly interacting massive particles. So these are things that have a weak nuclear charge and therefore have weak scale interactions with baryons. But then there are also things like sterile neutrinos, gravitinos, axions, like I mentioned, and things that generically get called hidden sector dark matter, but this is basically just any dark matter model that you postulate comes from some new symmetry and is not really connected to the standard model. There are bad options. Primordial black holes don't really work because, well, they can work in principle, but they're a very fine-tuned candidate. Massive compact halo objects were very popular in the past, but are now basically ruled out by microlensing searches. And they're baryonic, so they don't really work theoretically. And standard model neutrinos, in principle, have most of these properties, except that they're too hot, and they also give you the wrong relic density. Their masses actually are such that you come out with too small a relic density if you do the thermal freeze-out calculation. And you notice I've got the good, the bad, and then the elephant in the room, I guess, is the ugly that I haven't mentioned, and that's MOND. So in this particular section, I'm really focusing on WIMPs. Okay, so they're dark because they don't have any electromagnetic interactions, basically by construction. They're cold because they're quite massive, so they freeze out at non-relativistic velocities. They're non-baryonic and stable also basically by construction, so whatever theory you have that includes a WIMP, typically by hand you impose stability. And because they're weakly interacting, they have this weak scale self-annihilation cross-section. And what that means is that if they're thermally produced in the early universe, they naturally lead to a relative abundance that's about the same order of magnitude as we've observed in the CMB and other areas. And what I've shown here is basically a picture of how this occurs and then how the final relic density depends on the self-annihilation cross-section. Here you can basically think of the x-axis as time, so time is increasing going to the right, and the y-axis as the abundance of dark matter. So when everything's in chemical equilibrium, as the universe expands, the abundance of dark matter will follow this curve. But eventually you get to some point where the expansion outruns the annihilation, and annihilation is no longer efficient. And so that means that in co-moving coordinates, the number density of the dark matter particles freezes out, so it becomes basically constant. And that's what you see with these dash curves here. And depending on what the annihilation cross-section is, it'll freeze out at a different number. So a higher annihilation cross-section means that it'll freeze out with a smaller abundance. So it gives us a relatively strong constraint on the annihilation cross-section. There are lots of theories and candidates that can actually give you a WIMP. Supersymmetry is probably the most famous of them. So this is the theory where you have a super partner for every standard model particle, differing only by half a unit in the spin. But there are a bunch of others as well. So you can have extra dimensions, giving you Kaluza-Klein excitations, inert Higgs particles. There are various right-handed neutrino candidates, and so on. I won't really go into those in detail. The most important thing observationally really is that you have this weak interaction. So that means that there's a weak scale nuclear scattering cross-section. So it means that WIMPs interact with nucleons with a cross-section that is about 10 to the minus 36 square centimetres. It also means that since many WIMPs are Majorana particles, they have this self-annihilation cross-section, which is about equal to the weak scale. So this gives us two good ways to search for them. And in fact, you need both of these to search for WIMPs using high-energy neutrinos from the sun. And I'll show you why that is in the next few slides. All right, so how do you actually expect to get these high-energy neutrinos from WIMPs in the sun? You have the sun sitting in this halo of dark matter, right? And because there's a weak scale scattering cross-section between WIMPs and nucleons, you do expect some collisions between the dark matter particles in the halo and the nucleons in the star. So there'll be all of these collisions going on between the WIMPs and the nucleons in the star. In some of these cases, the collisions will be such that there's enough momentum transfer that the WIMPs have scattered to some velocity less than the local escape velocity at that particular height in the star. So they then become gravitationally captured, and it means that they'll come back on bound orbits, scatter some more, and eventually sink to the core of the star. So to get this to happen, you need this nuclear scattering cross-section, right? Now, because they annihilate as well, once they sink to the centre of the star, they'll annihilate with other WIMPs that have done the same thing. Typically, about 90% of the energy from that annihilation goes into heating the gas in the centre of the sun, or would go. But about 10% or so goes into high-energy neutrinos. So these high-energy neutrinos will be produced in the core of the sun and then propagate out. They basically won't interact with the rest of the sun, and they'll propagate directly in clean link to us here on Earth. The only interactions they should really go through in that period is oscillating between the different flavours. And what we can do is try to detect them using some kind of large neutrino telescope here on Earth. So the best way to do this is usually using a large target of ice or water and hope that you can get the neutrinos to convert into muons via charged current interactions and then look for the muons using Cherenkov radiation. So that's what the IceCube experiment is designed to do, and there are a number of others. Antares is a more local one, I suppose, and Subakamiokande is one of the best known. So the IceCube is, I don't know, one of the most interesting astroparticle experiments out there, I think, just because of the location, really. It's 86 strings of these optical modules sunk into the glacier at the South Pole. So it's basically a cubic kilometre of ice instrumented with these optical modules. So these detect the muon Cherenkov radiation that comes as a neutrino interacts in the ice and creates a highly relativistic muon. So there's about a gigaton of instrumented area, so it's a pretty big experiment. So what we've got then are a bunch of these optical modules lighting up from the Cherenkov radiation. So what I know then is the track of the muon, basically. So I have a bunch of information about the number of muons that are arriving from the sun, and from the track lengths or general topologies, I can also say something about the arrival direction and try to say something about the energy of the incoming neutrinos as well. So from the number, I can tell approximately how much annihilation is going on in the sun, right? So this tells me something about the annihilation cross-section, but most of all it tells me something about the nuclear scattering cross-sections, because it tells me how much is being captured in the sun. I have the spectrum as well, because I more or less know the energies of the incoming neutrinos via the muons. So this is sensitive to the WIMP mass, because heavier WIMPs, as they annihilate, will produce higher energy neutrinos. And it's also sensitive to what the WIMPs actually annihilate into. So if I annihilate into W bosons, I actually get a much harder spectrum of neutrinos out than if I annihilate into up bar pairs, for example. So this gives us potentially quite a bit of information about the interactions or the couplings of the WIMPs to different standard model sectors, which can tell us a lot about the particular theory that they come from.
Excuse me.
Yeah.
So can you put an example? So in which sense, depending on these branching fractions, you would expect these neutrinos with a higher energy, maybe. So then from the muon tracks, more or less, you can try to reconstruct them.
Yeah, exactly. So, I mean, you're not going to do it on a single event basis, but statistically, if you have a heavier WIMP, you expect higher energy neutrinos. And if you annihilate to a harder final state, then you expect higher energy neutrinos. So in that case, it's a matter of how the particular standard model particles that you annihilate into decay and interact with the other particles in the sun. So W bosons, for example, will decay directly to neutrinos with a very short lifetime. So if you annihilate into W bosons, then you should produce a lot of high energy neutrinos from the decay. And I guess the most extreme example is if you annihilate it directly into neutrinos, because then you'd basically have a neutrino line, a monochromatic line. And you also have information about the direction, which tells you how likely it is that these things have actually come from the sun rather than come from interactions in the atmosphere. So, I mean, normally when you see these sorts of analyses, looking for these sorts of signals, people just assume that the dark matter annihilates into some particular final state and just place limits under that assumption. So they have a whole bunch of different curves for different final states. And typically you're only looking at the arrival direction of the neutrinos and the total number. You don't consider this spectrum. So what we did was to set up basically a likelihood formalism where you could take any particular model that gives you any combination of annihilation branching fractions and then uses all of the individual event information including the energies, to say how likely that particular model is. So the idea here was to be able to use this likelihood in detailed scans of specific beyond the standard model theories. So in that case, you would step through the particular theory you're working with, say like supersymmetry, and be able to really directly compare the neutrino events seen by IceCube to the specific point in the model parameter space you're interested in. And all of the examples I'm going to give are from supersymmetry, but it's really a framework that you can use for any model. And correspondingly, it's available publicly. So all of these routines for doing this event level likelihood analysis, as well as the actual IceCube data that we've used, are available publicly as part of the Dark SUSY package. And yeah, the IceCube data is available on a dedicated web page as well. Okay, so I mean, how do we actually construct this likelihood? I'm not going to go into all of the gory details because that gets pretty technical, but it's probably useful for you to at least see the number part of the likelihood. So the simplest way to do any of these sorts of experiments is just to turn them into a counting problem, right? So you ask, how likely is it that I'd see this many events if my particular model that I'm working with predicts this many? And that's essentially what this number likelihood is here. So it's the likelihood of getting n observed events given theta sig predicted signal events and theta bg predicted background events. Now, we know theta bg actually because we know how much background there is looking just away from the sun. So this is actually observed already. And then this likelihood is actually just a Poissonian likelihood, which you may be able to see here with this n factorial and e to the theta and theta here. But it's convolved by a PDF describing how we think the effective area of the instrument is known. So this accounts for possible systematic errors. So this includes the uncertainty on the effective area of the instrument.
That is Gaussian, right?
Sorry?
So you put that in a Gaussian model?
No, this is a log normal actually, but you could do it as a Gaussian as well.
It's epsilon.
Sorry?
It's epsilon, the parameter is epsilon.
Yeah, exactly. Yeah. So you effectively marginalise over this epsilon parameter. The reason we do it with the log normal is just that you want it to actually go to 0 as epsilon goes to 0, which isn't necessarily the case for a Gaussian if you have a large width. So in the case of IceCube, the width of this epsilon parameter is about 0.2 or so. So it doesn't make a big difference whether you use log normal or Gaussian. So this is just the number component. There's then another big sum that goes over every event that takes into account the energy of each event and the arrival direction of each event. And I'm sure you don't want to see all the details of that, but you know at least that it's there now. I can show you the details later if you're really interested. Okay, so the very simplest way of doing these sorts of scans is to just do a simple, dumb, random scan and just compare the number of events that you would expect from the different points in the parameter space to the number that could be observed. And this is what we did in the third paper that I showed you at the beginning. For the case of a 25 parameter version of supersymmetry. So here I've got the spin-dependent scattering cross-section between WIMPs and nucleons against the lightest neutralino mass, so this is the dark matter mass. And here I have the spin-independent nuclear scattering cross-section. So these are typically the two different interactions with nucleons that people look at. One that depends on the nuclear spin and one that doesn't. The different points show the points that turned up in our random model scan according to how strongly we can exclude them using the full IceCube detector. So the things in blue are the things that we can exclude at better than 5 sigma, whereas the things in red are those that we really can't get at with IceCube at all. And then these different curves show the best sensitivity so far from different direct detection experiments. So you can see here in the spin-dependent plane, we're actually going to do a lot better with IceCube than pretty much any direct detection experiment. Then even in the spin-independent plane, which normally the searches for high-energy neutrinos are not considered to be especially sensitive to, there are a lot of models here that we'll be able to get at with IceCube that are really pretty much never going to be accessible with direct detection experiments. So you can see these ones down here in blue and in light blue as well. So, I mean, that's nice, but this doesn't tell us in any sort of overall statistical sense, like how much of the parameter space we can get at. This is only on a point-by-point basis. I can say for each point how strongly I'll be able to exclude it. But
what about in the spin-dependent, what about the points between let's say the blue line, more or less, horizontal, and the limits from other experiments? So you also exclude those points which are now in white. So
Sorry?
the points, you see the blue more or less horizontal line?
this one,
Exactly.
yeah.
So between this line up to this line,
Yeah.
why you cannot, so you haven't calculated that, or you expect to exclude also with a high...
It's because there aren't models in our database
okay.
that come up there. If you worked in another model, as in like not this MSM25, then you could probably find models up here. And in principle, you could, I mean, in some parts of the MSM parameter space, maybe you could find higher cross sections as well. Depends on the details of your scanning procedure.
So you said different colors mean different significances?
Yeah.
Then why do you have, for example, like the red getting into the middle of the colors, and why do you have these strips going down and nothing in the white? It's just scanning?
It's just scanning, again.
Because I would expect like a smooth...
Right, you would if...
This is cross-sectional mass. This
Yeah,
has nothing to do with the model from that point of view.
Well, it is, that's the thing. The sensitivity of the experiment actually really depends on the spectrum of the model that you're
Sure.
looking at.
Sure.
And that's why it's often misleading when you see people plotting specific curves in this plane for these sorts of high-energy neutrino searches. Because it depends very much on the annihilation spectrum as to how strong the limit will be. So these points, right, there are a bunch of red points behind them. So you can get a model with the same overall nuclear scattering cross-section and mass, and depending on what it annihilates into, you'll either be able to see it or you won't.
Right, but these are very high masses. This is 1 TeV, so whatever the channel is going to be above threshold, even if you have a short channel.
Sure, I mean, things can be
argument
open.
when you go to low masses, because you might miss some of the soft channels, but when you want to verify masses, you will always see. Obviously, you will probably lose some sensitivity, but still, you do see it.
Well, you won't necessarily see it. It depends on the total fractions, the actual branching fractions into the different final states. So even though you might have all of the channels open, it doesn't mean you'll have a significant branching fraction into every final state. They'll all be allowed.
Oh, that's right.
But many of them will often be
That's
suppressed in different parts of the
because in
parameter
this case,
space.
there are some channels which contribute nothing.
Exactly. Exactly. And, I mean, you can have cases, like I say, the red points behind these, where the best channels will contribute nothing, or you might dial them up and dial something else down, and then it'll be a lot more detectable. So, I mean, it is a little bit tricky sometimes to interpret these sorts of things. So you have to be pretty careful. And, I mean, that's why you actually need to do more detailed scans where you do basically a full statistical interpretation, which I'll get onto a little bit later. Here we have the same scans, but then compared to limits from different LHC experiments. So here we've got the neutralino mass versus the gluino mass, and then the lightest squark mass versus the gluino mass. And the areas to the bottom left of these curves have been excluded in a specific SUSY scenario by different LHC experiments. So, even these curves really should be different depending on which model exactly you're talking about. And I guess the take-home point from these is that you see that the models that we can get at better than 5 sigma are not really clustered anywhere in these planes. So there's a large degree of complementarity here, because the LHC experiments preferentially will get to models down towards the bottom left, whereas IceCube will get at different models all over the place here. There'll be models that it can't get at all over the place as well, but the point is that it's quite complementary. Okay, so like I said, what you really want to do if you want to start talking about, you know, how much better one model is compared to another, and then what parts of the parameter space are allowed and which ones aren't, is to do a full-blown statistical analysis, basically a global fit. When you do these simple in-out analyses, you can only say on a point-wise basis whether a particular point is allowed or not. You can't generalise to the whole parameter space or even whole sections of the parameter space, because you need to define some kind of metric on your model. In order to do this, you really want to basically calculate the likelihood for every point and roll this into a composite likelihood setup. And this is what I mean by a global fit. Once you've done that for every point in your parameter space, you can then look at either the profile likelihood, which is the maximum of the likelihood in all of across the different directions in the parameter space that you're not interested in, or you can look at the posterior probability density function, which is essentially just the integral of the probability across the directions you're not interested in. So what we typically do with this is to make up this composite likelihood from a whole bunch of different experiments. So we take the observed relate density from the CNB. So we have, you know, a particular number and an uncertainty for that. We have different precision electroweak tests at LEP. We have limits on the masses of the superpartners. We have all kinds of limits on rare processes from B physics. We also have the observed anomalous magnetic moment of the muon, which can get contributions in loops from superpartners. And then we also have the LHC and the direct detection likelihoods, which are probably the most active area of research in global fits at the moment, because there's so much new data rolling in at the moment. So what we did was to basically put this event level IceCube likelihood in with all of these other experimental constraints, and then look at the overall marginalised posterior PDF in different parts of the parameter space. So in this case, I'm actually looking at the constrained MSSM, which is just another parameterization of supersymmetry. It has 4 free parameters and 1 free sign. But what you really want to look at here is the difference between the contours in black and the ones in grey, which is not really very much. But the ones in grey are the fits including all of the pieces of data that I just talked about. And then the coloured ones are including all of those plus 22-string IceCube events. So you can see here in both the spin-independent scattering cross-section and the spin-dependent scattering cross-section that including the 22-string IceCube data doesn't do an awful lot. But you can see that at least our likelihood formalism is working. And you don't expect the 22-string IceCube data to have done that much, because that's only about a quarter of the detector. What you can do instead is look at what the full detector will be able to do for you. And I should say the reason we're not looking at full 86-string IceCube data is that it's not available yet. They only just finished making the detector. So we will go on and do that once the data is available. But okay, so here is those 3 plots again. So spin-independent scattering cross-section, spin-dependent scattering cross-section. And here, 2 different masses, fundamental masses in the theory. So these are just particular Lagrangian parameters. And I'm going to show you what happens to this parameter space as I add in different constraints, basically. So here's what happens if I include Xenon 100's constraints. And you see that I shave off some of the highest spin-independent scattering cross-sections, as you might expect, because that's what direct detection experiments like Xenon 100 are most sensitive to. You can get at some of these spin-independent scattering cross-sections and get rid of a little bit of this area, but for the most part, it's not a huge constraint. If you include some of the latest results from CMS on searches for super partners, you see that you get it this area here, which is, if you know the terminology, the Stow correlation region. So you cut out about half of that, but there's still quite a large amount of parameter space that's viable. If you then look at what IceCube will be able to do once it's finished and we can access the full data, you can see that you can actually do an awful lot more. So IceCube can really rule out a big chunk of parameter space here in combination with these other things that you couldn't do without also including IceCube.
So when you say IceCube, you also mean DeepL, right?
Yes, exactly. What we've actually done here is just taken an IceCube 22 effective area and scaled it up by a factor of 100, because you don't know exactly what the IceCube 86 effective area will look like. And there's also other information that we use, like the energies and the arrival direction. So basically the energy dispersion and the PSF that we still don't know for IceCube 86. So this is a little bit rough in that sense, but it's the best prediction we can make.
So these constraints on these parameters are assuming that IceCube detects no high energy muons from the muon.
Yes.
So it's impressive how well you can constrain the theory that explains your dark matter candidate detecting nothing.
Yeah.
So if IceCube detects some of these significant events on this high energy from these high energy neutrinos, how much? I mean, that's not the work you did here, but how much better will you be able to identify the underlying parameter of the theory?
We actually did do that. So that's the next slide. We injected a specific model and looked at how well we'd be able to recover that. And you can see that it's actually quite tight. So this is a 500 GeV WIMP annihilating 100% into W plus W minus, which we just assumed produced 60 signal events. So, I mean, you can look at this in terms of the predicted number of signal events from different models and the mass, and you see that, you know, you constrain the mass to be between maybe 100 and 600 or so, which, you know, considering the fact that, well, in these coloured contours there's no energy information, sorry, in the grey contours there's no energy information included at all, and then in the coloured contours we had the energy information included. That's pretty good, really. We use one particular realisation, so there's some, you know, statistical noise in here. So our reconstruction comes out about on the one sigma contour, which is, you know, not that unexpected. If you look at it in terms of the nuclear scattering cross sections, you can see you can really narrow them down to basically within a half an order of magnitude or so, which, if you compare to how they were before, that's a good, like, factor of 100 improvement in your determination of these values. And you can see also that when you include the energy information, it helps a lot. So there's a fairly significant chunk of the parameter space here in grey that we exclude by including the energy information. So how much time do I have left?
Well, I think 15 minutes.
Yeah, including questions or
Without questions.
well, okay, cool. All right, so the next thing I wanted to talk about was this idea I mentioned for potentially fixing the solar abundance problem. The solar abundance problem, or depending on what you want to call it, solar modelling problem or solar oxygen crisis or whatever, is basically that in recent years we've had about a factor of 2 downwards revision in the chemical composition of the sun. And this has really come from an improvement on many, many different fronts. So we're pretty confident that this downwards revision in the photospheric abundances is quite robust. We've had significant improvement in the atomic data that we've used for different elements. We've also had more accurate equivalent widths that we've been using. 3D modelling of the hydrodynamics in the solar atmosphere. A bunch of non-LTE corrections, which have involved a hell of a lot of work by, well, a lot of other people that I'm very thankful to. And, you know, one of the reasons that we think it seems to be correct is that we have a substantially improved agreement with the abundances observed elsewhere in the solar neighbourhood. Whereas before this revision, the sun was thought to be somewhat anomalous chemically. However, this downwards revision, if you go and plug it into helioseismological models, screws basically everything up. If you use the new abundances and look at the sound speed profile, which is what I've plotted here as a function of radius, you see that with the old abundances here in black, it's more or less correct. If you looked specifically at the error bars on here, you'd see that at the base of the convection zone here, it's still a significant discrepancy, but everywhere else, it's more or less within errors. Whereas if you use the latest abundances or even the next to latest abundances, you can see that this discrepancy grows substantially. And if I remember correctly, it's about a 50 sigma discrepancy with this 2005 set of abundances. And I think it might have been almost 10, however, with the older ones. So even with the old abundances, something was a little bit fishy here at the base of the convection zone. But now with the new abundances, it's disastrous. So people have really been trying their guts out to solve this in every way imaginable. They've tried all kinds of modifications to helioseismology with new opacities, late time accretion of low metallicity matter. People have also looked at the influence of gravity modes. People have also tried to see if some solutions can be found using different 3D model atmospheres. None of these things have come up with viable solutions. So, I mean, it could be that there's still something, well, it must be that there's still something we don't understand, but it could well be that there's still something in spectroscopy or helioseismology that we don't understand. But considering the amount of effort that's gone into this so far, and you know, the fact that that effort's been going on for the last decade or so, I think it's probably fair game to start thinking about new physics solutions to this.
Is this the abundance of the whole sun?
Yes.
So these are the abundances in the whole sun, right?
Yeah. I mean, that's one of the potential, you know, reasons for friction. The spectroscopic abundances are photospheric abundances, whereas the helioseismological models care about the core abundances most of all. So we think we understand how abundances should vary from the photosphere down to the core, just through diffusion and settling and so on. It should be a difference of only about 0.04 dex. So it's nowhere near enough to account for this discrepancy. But this is why things like late time accretion and low metallicity gas can potentially help, because you just, in that case, you artificially put some low metallicity stuff where we're seeing the spectrum form.
How this uncertainty impacts in the calculation, for example, of the capture rate?
It's not, it's subdominant compared to all of the astrophysical uncertainties in terms of the dark matter halo. Most of all due to the velocity distribution in the dark matter halo.
Maybe still independent could be.
Yeah. In principle, it's up to a factor of 2. But we have more than a factor of 2 uncertainty coming from the velocity distribution of dark matter locally. And we have almost that much uncertainty even in the local density of dark matter.
But just a comment. I think what is the big problem is the fact that you cannot measure actually the opacity in the equations. All opacity that's theoretical. And even if you get the abundances correctly, you know, it's very easy to make a mistake. And I think there are some labs that are preparing now to really go to the lab and measure the soup more identical, and then you could very comfortable strength.
Yeah.
Because it actually is, if you go to the 8s, then the 9s is always the same problem. Opacity is always bring problems to or equation of state to have a seismology. It's actual seismology has contributed a lot to the equation of state and to radiation to progress. And again, I'm not saying it's that, but at least you need to put that out of the
exactly. I mean, people have found that you need to change the opacities in the core by of order 30%, and at least theoretically, the conclusion was that you can't do this. If you go and look at the calculations from the Iron project, for example, there's just no way to get this 30% modification in the opacities. But it's still entirely theoretical, right? Like they could have missed something.
A help could come from neutrinos, from the solar neutrinos, from the CNO cycle, that will be sensitive to carbon and oxygen and fuel and so on. And then eventually you can do what you were saying. For the first time, run out assuming that the photosphere are the same as the primitive cloud, and eventually now you can at least in some reactions say, okay, the Z or carbon around 0.3 of the solar radius is more or less that. This would be amazing in the sense that you can calibrate.
Yeah, I completely agree. I mean, I think that's the best hope we have for resolving, well, for at least understanding exactly what the abundance is in the core. Yeah. Basically when Snow Plus gets going. Yeah. But like I said, until then, we can play around with new physics ideas for potentially solving it. So the idea we had was that maybe if you had axions being produced in the photosphere, you could have photons oscillating into axions in the line-forming region, and therefore instead of being absorbed by the different atoms there, they'll pass straight through them. And to a very good approximation, when you look at how the different radiative transfer codes are set up for working out what these line depths will be in the absorption processes, this plays exactly the same role as an additional opacity. So it's like artificially increasing the opacity in the lines, and not in the continuum. So what actually matters most of all is the contrast between the continuum opacity and the line opacity. So it's a specific increase of the line opacity, which would then change the abundance that you would infer from this line.
Do you choose specific say frequencies where the lines occur, or generic? When you talk about lines, is specific for each one of the kind of action you consider, or
it actually happens across the spectrum, but it's only the line opacity that it changes rather than the continuum opacity.
Okay.
So it happens in a kind of a continuum way. But I mean, this is essentially what I'm showing here. But it happens because the lines form higher than the continuum. So if you tune the axion parameters, you'll have the conversion occurring preferentially at higher layers than the continuum is produced at. So you basically want to set up your axion-like model such that you mostly get this oscillation where the lines are forming but not where the continuum forms. So here I've shown a couple of examples for axion-like particles with a couple of different combinations of parameters. Now, there are a couple of different regimes that you might be interested in looking at. One is where you have resonant conversion from axions to photons, and you enhance the conversion rate. And that basically just occurs where the mass of the axion hits a resonance with the plasma frequency. And it turns out that even though that's the best hope for achieving this sort of effect, you can never really get resonant conversion in the line-forming region. You can only get it at about the continuum forming region. So this set of parameters is selected to get the strongest resonant conversion that we can get. And basically the best we can do is a 0.05 dex change, which is nowhere near enough. We need about a 0.2 dex change to reconcile the photospheric and seismological abundances. These dashed curves are the contribution functions from two of the most commonly used carbon and oxygen lines, and they just give you an idea of where these lines are formed. So you really want to try and get some contribution that's large-ish where this is large. But you can see, yeah, all of this is down very low, and it's not large enough at all. The other thing you can then sort of hope to do is to go for non-resonant axion production. And in this case, you have a basically constant probability of oscillating from a photon to an axion. But the impact on the abundance as a function of height in the atmosphere, which is shown on the top axis, goes up as you go further in the atmosphere just because the overall opacity is going down. So the axion opacity is basically the same, but as a fraction of the overall opacity, it's going up. And that's why you get this increase over here. So you can see that with these particular parameters, we can get up to about the right sort of change in the abundance. So over here, I've plotted this delta log in the abundance. So the goal is to get up to around 0.2 or so. However, these particular parameters that we've used are horrifically, that we had to use to get this, are horrifically ruled out experimentally for axion-like particles. And that's why I say this really doesn't work. So here I've shown all of the different constraints on axion-like particles in terms of the mass of the particle and the coupling. This is basically the coupling between axions and photons. And you see that the coupling we need to make this work is way up here, so it's horrifically ruled out by all kinds of other things. So, you know, you can't do it with normal ALPs. You would need some other kind of light boson that could do this oscillation from photons into the new light boson, but it would need to somehow be able to skip around these different constraints. And these are not all based on the same physics. So in principle, this might be possible, but it's pretty hard considering how badly ruled out it is. We thought about whether you could do the same thing with some related theories. So chameleons, these are also light bosons that oscillate into and out of photons that have been postulated to solve dark energy and dark matter at the same time. We also looked at hidden photons. These are basically just another photon with a gauge group similar to electromagnetism. But the long and the short of it is that even when you recast these limits in terms of chameleons and hidden photons, you can't do it. So our conclusion really is that, you know, none of the well-known theories of light bosons can explain the solar abundance problem. Okay, so I hope I and Geordie earlier today have convinced you that the sun's, you know, pretty useful for particle physicists as well as astronomers. And, you know, there's a lot we can do with these searches for high-energy neutrinos from WIMP annihilation in the core of the sun. We've got this event-level likelihood module available now in Dark SUSY, and so you can really start to do serious statistical analysis of different beyond standard model theories using that. We have a 79-string IceCube analysis coming up that should give some very competitive limits. And, you know, I've shown that there are a whole bunch of different models that IceCube 86 will really be the only experiment that can access. And then I told you a little bit about this idea for solving a solar abundance problem, but okay, it doesn't work, but it was something that needed to be tested anyway. And I think that my point holds that it's kind of fair game now for particle physicists. Thanks.
I have a comment.
Mm-hmm.
So when in the WIMP searches, yes, a comment. It's like this high energy neutrinos can only be, and we touched upon this in the question. They are only produced from heavy quarks, gauge bosons, and annihilations into heavy quarks and gauge bosons and tau.
You can actually get them even from annihilation into the lightest quarks.
If you have very high, from only very high dark matter masses.
Yeah, reasonably high.
Low masses are 100 GeV or 200 GeV produce low.
The yields are small, they're not zero though.
They are not zero, but the yields are never zero in any case. So I would like just to stress that in the case, for example, of dark matter mainly annihilating into muons or into light quarks, these searches have no result. There is no high energy neutrino. But there is a possibility to use.
I don't really think that's true, actually.
That is true.
No, if you look at, say, like cascade interactions.
No. So dark matter annihilation into muons, mainly into muons, produce no high energy neutrino at all. Muons get absorbed.
Sorry?
So there is no high energy neutrino.
It's in the interaction in the sun that you produce the neutrinos. If you produce a really high energy muon, it'll interact, and in many cases it'll create some kind of highly unstable meson, which can then decay by neutrinos.
But the muon doesn't interact in the sun. I mean, it goes to rest like without this density. I mean, it's so high.
Yeah, but that's how you produce most of these neutrinos anyway.
Sure, but what I'm saying is that you can. I mean, in principle, you could think that could happen, but in fact, it doesn't. That's what I'm saying. That a muon, a 100 GeV muon, will go to rest, producing this very, as I said, the number is exactly never zero, but basically producing no high energy neutrino at all.
I mean, there's been work on models designed to explain Pamela, for example, that annihilate almost exclusively to muons, and then
we can check that, but I'm 100% sure what I'm saying. So, but in those cases, and even if you're annihilating to electrons, it's even worse. Obviously, because there is no, you would have basically you could use the same argument that we said that they go basically to rest. And in the case of light quarks, unless you go to very high masses, the problem is the same. Now, the comment I wanted to make, and the point is that in those cases you can search for those low energy neutrinos from these particles when they go to rest, they will decay. The muon will decay and produce low energy neutrino, and those can be searched. Super clear. These are tens of energy neutrinos, and these can be searched. And actually, they put limits not as constrained as this, but in those cases where you can put this kind of limits, those are complementary searches.
Yeah. I mean, the problem you have then, though, is that you have the potential to mix them up with the actual normal solar neutrinos.
No. Solar neutrinos are lower energies. This is muon decay neutrinos. So these are tens of MeV. So this type of search is like the diffuse supernova neutrino search. Tens of MeV neutrinos, about 10, say about 20 MeV. So there is no solar neutrino. Actually, the solar neutrino is a background, so you have to go away from it. It's like exactly the same as the same window you would search for the diffuse supernova neutrino. It's just there are cases where you don't produce high neutrinos, but you still have a neutrino signal and low energy.
I have a question regarding your first part about solar neutrino telescope data. Correct me if I'm wrong, but the study that you showed us was on a model that had beyond standard model that had 4 parameters in each other. If you increase by an order of magnitude that number of parameters, I would expect that you can exclude less because you have more channels. Is that correct?
Yeah, in a general sense, that's kind of correct, but it depends on the model. I mean, if you increase the parameters in such a way that all of the new parameters lead to higher fluxes, then you be able to exclude more of it. But in general, as you go to more general MSSM models, then there are a lot more models that you can't get at.
So if there are no further questions, thank you, Pastor.
worries.
just stop the recording.